First presentation for today's showcase event is by Arash, and as you can see, Arash is working with us here at Imperial College London in the turbulence simulation group. And I thought it would be nice to start with Arash because this is a brand new software development that we have done in the last couple of years by Arash, and also a lot of work by Paul Bartholomew, who is now working at Edinburgh, but he was working in our group for a couple of years. And basically, now we can do what we call a quasi-compact flow setup. Is basically, we can solve the compressible Navier-Stokes equation in the low Mach number limit. That was a very old code developed by Eric Lamberlet in Poitiers 20 years ago, but now it's fully parallelized, fully optimized, and we can do some really nice stuff. So Arash is going to talk about that. So please, Arash, go ahead, 15 minutes.
Thank you very much, Sylvain. As Sylvain mentioned, I'm going to talk about direct numerical simulation of Rayleigh-Taylor instabilities. And this work is done, has done by me, Paul Bartholomew, and Sylvain. About the Rayleigh-Taylor instabilities, they develop at the interface of two fluids when the interface is subjected to relative acceleration, such as, for example, gravity. They are typically multimode, which means that they are formed of many individual instabilities or single mode instabilities. For example, here on the top right, you can see many individual instabilities forming this multimode instability. RT instabilities typically are characterized by Atwood number, which is essentially the ratio of the densities of the heavy and light fluids. They can happen in across various scales from and many industrial applications and in natural in nature. For example, here we can see a complex polymeric elastic surface created by RT instabilities, and here is the mammoth clouds, which are believed to be formed based on such instabilities. So an overview of this study. So as Sylvain mentioned, we developed a two-phase flow capability for X-compact 3D. Here in this specific talk, we're going to study the effect of various Atwood numbers, Reynolds number, surface tension, and initial perturbation amplitude on Rayleigh-Taylor instabilities, and we're going to make a direct comparison between 3D single mode and multi-mode instabilities. Regarding the X-compact 3D framework, as many of you are familiar with, it has a high order compact quantum difference discretization scheme for Cartesian grids. Here we are using a variable coefficient Poisson pressure equation in order to deal with the pressure velocity coupling, which gives us a spectral-like accuracy. And the framework is highly scalable, and because of its very efficient 2D or pencil decomposition based off this 3D decomp and FFT library. Starting with the governing equations, we are using the one fluid or mixture approach, which means that we just solve one set of equations for two governing equations for two fluids. Here we have the continuity, and the second equation is the momentum. And in order to track the phases or the interface, if you like, we use a method called the phase field method. It has different formulations. Here we use the Allen-Kahn formulation, which is essentially a advection diffusion equation with a second order diffusion term, except those terms that are highlighted in green. The rest are discretized using the sixth order compact scheme. The green ones are related to the gradient of the phase function, which is not continuous, and we use a fifth order Vino scheme in order to obtain a smooth solution. And for the time, we use a two-step explicit Allen-Backward discretization. Regarding the initialization of the domain for both 2D and 3D single mode instabilities, we initialize the domain by applying a initial cosine perturbation with this formulation, as we can see here. But for the multimode one, we apply the perturbation to the vertical component of the velocity vector. And the reason for that is that because it has been shown that for such multimode instabilities, this kind of perturbation which will give us almost grid independent perturbation. Starting with the 2D RT instabilities, as you can see on the top in the right figure, the initial perturbation grows exponentially and forms this spike and bubble feature. The spike rolls up after a while and creates these tip vortices, and then the tip vortices evolve and then form the secondary vortices, which then evolve into a complex turbulent feature. The interface remains symmetric despite its complex feature, and here we compare it with against the penetration length of the spike and bubble, the absolute values, against the data from the literature, and it compares very well. With regard to the grid, we conducted a grid study, different grid resolutions. As you can see, except for the very coarse one, the rest, the penetration lengths are not that different, and the main difference is, in fact, is inside this turbulent wave of the tip vortices. Based on this result, we decided to continue with a medium grid size for both 2D and 3D single mode instabilities. So we first studied the effect of the Reynolds number. From the left graph, you can see that changing the Reynolds number doesn't really change the penetration length of the spike and bubble that much, except for the very low Reynolds number, which has a slightly different penetration length. The rest, from 1,000 to 10,000, they exhibit the same penetration length. But the main difference on the right graph you can see is in the topology of the instability. By increasing the Reynolds number, you get more complex flow features and roll up of the spike. And when you increase the Reynolds number to 10,000, you get perturbation of the bubble, which you don't see in the other cases, and this is due to the Kelvin-Helmholtz type instabilities. After the Reynolds number, we study the effect of the surface tension. So we pick two Reynolds number values. We increase for the 3,000 Reynolds number. We have the cases with the surface tension equal to 0. This specific case, which is highlighted by this dashed box, is a case that doesn't have a surface tension, but we remove the diffusion term of the phase function. And as you can see, changing the surface tension in this low Reynolds number doesn't really change the topology of the instability much. And here we conclude that if you have a low Reynolds number and low surface tension, we can even neglect the diffusion term of the phase field function, and it can save us some computational time. But for the high Reynolds number, when we saw a bubble perturbation, if you have a strong surface tension, then that is suppressed and you don't get such bubble or spike perturbation. So high surface tension can suppress those kind of instabilities. Then we move to Atwood number. We increase the Atwood number from 0.2 to 0.75, and as you can see, by increasing the Atwood number, the penetration length of the spike increases and the penetration length of the bubble decreases. Also, on the right figure, you can see that by increasing the Atwood number, the complexity of the tip vortex of the spike reduces, and you get less turbulent structures. And this is because you have a higher velocity of the spike, then which requires a higher force to roll it up. So when you increase the Atwood number, you get less strong vortex tip. Then we calculate the velocity of the spike and bubble, and then we see that they reach a kind of terminal velocity before they reaccelerating again. And this terminal velocity is, which are shown by this dashed line for the correlation suggested by Goncharo. Our simulations are very well in line with that prediction, but then they reaccelerate. And such reacceleration is because of the formation of the complex vortex at the tip of the spike, and which reduces the drag. On the right, you can see this correlation, which we came up with, is actually relates to the vertical direction of vertical distance of the spike and bubble versus the Atwood number. And for example, at different times, you can see that this correlation predicts the DNS data very well, although it has 4 parameters, but if you see here, the difference is only in eta, which is the adjustment parameter. So this correlation can predict this vertical distance very well. Now we move to the 3D cases. For the 3D cases, again, the same behavior, but we have another feature which we don't have in the 2D. It has the 3D case has a feature called the saddle point. And again, combined with the literature data for the spike and for the bubble and also for the saddle point, they match very well. And the 2D tip vortex we saw previously for the 2D cases now appear here as a vortex ring in the 3 dimension. And one other thing that we can, if you compare this graph with the previous ones, we see that for the 3-dimensional test, it penetrates more in comparison to the 2D case for a similar Atwood and Reynolds number. Then we studied the effect of the Reynolds and perturbation amplitude. And again, similarly to the 2D cases, we realized that changing the Reynolds number doesn't really change the penetration length of the spike and bubble or the velocities. But then perturbation amplitude has a significant effect. And as you see, if you have a very small perturbation amplitude, then this black line here, it doesn't even grow exponentially like the other two. And the other interesting thing here, we realized that for the 3D cases, only the cases with very high perturbation amplitude, the bubble reaccelerates, which actually we can then conclude that the 3-dimensional cases require a higher initial perturbation to show such below reacceleration, or if you like, non-linearity. And then we study the effect of the Atwood number. Again, we see the same behavior as we saw for the 2D cases, and with the addition of the saddle point, which behaves in a similar trend as the spike. Again, the velocities for most cases reaccelerate for the bubble and the spike, and for those 2 cases that they don't, because they reached the bottom of the domain within the length that we studied. That's why it doesn't show such flow behavior. And in this graph, we study now on the left the interface area of the 3D instabilities, and we can see here by increasing the Reynolds number or reducing the Atwood number, you get higher interface area. And it is because you have a more complex turbulent flow feature, which actually creates a wider instability, which you will see in the next slide. And on the right, you can see that the previous correlation that we proposed for the 2D works also for the 3D cases, but with a slightly different, if you can see, coefficients here, the power of the Atwood number is 4 instead of 2 that we have for the 2D cases. And this slide was the one that I just mentioned. When you increase the Reynolds number or you decrease the Atwood number, you get a stronger tip vortex ring and a slightly wider instability. That's why you get a higher, a larger interface area, as we saw in this graph. And now we move to the 3D instabilities, multi-mode instability. We make a direct comparison with the single modes one. As you can see here in this area is the ratio of the interface of the instability over the area of the domain. And as you can see, they both, the single mode and multi-mode, they behave almost the same for the very beginning, but then the multi-mode one, the interface stops increasing and reaches some kind of a plateau before increasing again. And this is believed to be due to the mixing and collapsing and merging of the individual instabilities. As you can see, for example, here in this video for the single mode instability, they grow and then start merging after a while. I think I can probably bring this one. If you can see, this is a bigger video. So as you see, they grow. We have this single mode, almost like instabilities, which then they merge and get elongated and form complex shape instabilities, which then they grow, but with a slightly different rates. So from here, we see that the effect of the single mode instabilities is very important on the multi-mode instabilities. And the conclusion here is that we developed a phase field model and implemented it in X-compact 3D. We studied the two-dimensional, three-dimensional, single mode and multi-mode incompressible immutable Rayleigh-Taylor instabilities. We realized that the surface tension can have a significant effect. When you have a high Reynolds number, it can suppress the instabilities. And for both 2D and three-dimensional instabilities, we noticed the reacceleration of the spike and bubble velocities. And then we realized that the three-dimensional instability may require a higher initial perturbation amplitude in order to exhibit such reacceleration. And we propose a new correlation for the vertical distance of the bubble and spike versus Atwood number. And by comparing the single mode and multi-mode three-dimensional instabilities, we realized that the behavior of the individual single mode instabilities of a multi-mode instability is really important in the overall behavior of a multi-mode instability. Thank you very much for listening.
Thank you very much, Arash, for your presentation. Bang on time, so that's a good start. There is a couple of questions that have popped out on the chat, and please, if you have questions, add your question to the chat. The first question is, can you tell us again what method is used for the interface reconstruction?
Okay, we didn't actually reconstruct the interface, and as I mentioned here, it is kind of a diffuse interface approach based on the phase field method. So the interface is actually treated by the diffusion term on the right-hand side of this transport equation for the phase function. So it is not a sharp interface approach like VOP or like level set. It is a diffuse interface, which is called the phase field approach. It has different formulations like Allen-Kahn or Kahn-Hillard equations. We use this one because it has a second order diffusion term. It's easier to implement and handle.
Thank you very much. Can you tell us about the boundary condition on each side?
But boundary conditions here, we use a slip condition, but we can use periodic one. I tested for the length that we studied here, both produced the same result for both 2D and 3D cases.
Okay, and there's another question about post-processing. Is there any plan to connect the analysis and the amplitude of the perturbation with modal analysis? The rationale is that stable modes can exhibit transient growth.
Yes, I mean, we actually have plan to run further three-dimensional multi-mode instabilities for different Atwood numbers, and probably to do some further analysis on that. But at the moment, we don't have the data. But probably in the future, we will perform some more studies. But good idea. Thank you.
Thank you, Arash. Can you
Thank
show us
much.
the movie again, as we have a
yes, sure.
Sure. Nice
let me just bring it here. So this is the start again.
Very nice.
Thank you very much.